All right, so we did cover most of this, well, up to the integral stuff, right? So just to remind you, if we have a parametric curve defined in terms of x equals f of t and y equals g of t, then we said that we can find the derivative dy dx by dy dt over dx dt. And then the second derivative is going to be d dt of dy dx over dx dt. We did do an example with that. Sketched out a parametric curve, look like that, and we kind of analyzed a bunch of points of it. Found its horizontal tangents, found its vertical tangent at 0, found that it has two different tangents at one point, at the point 3, 0, and found the equations of those tangent lines. All right. So this, I believe, is where we did not get through, and that was finding area. Oh, no, or did we? We got through this, didn't we? Oh, no. Okay, we did get to some of the integral stuff, huh? And we did example 2. We found, yeah, because we found that the area under one arch of the cycloid ends up being 3 pi r squared. We didn't do arc length and surface area. Okay. So let's move on to arc length. And so here's our general arc length formula for some curve y equals f of x, where x is between a and b. And we're going to suppose that our curve C can also be described by the parametric equations x equals f of t and y equals g of t, where dx dt equals f prime of t, and that's greater than 0. All right. So then I'm just going to make a substitution here. Which is, we already knew that dy dx was this, dy dt over dx dt. All right, and then you can kind of see here with cancellation that I'm replacing my dx with dx dt dt. So basically these differentials would cancel and leave me with just the dx there, which is why that's a valid substitution. Since I'm now integrating with respect to t, my limits of integration become alpha and beta, which were the parameters of t for tracing out the curve. And I can actually simplify this to a much more kind of intuitive integral, which is, if we look at that integrand, we'll kind of do the algebra of it off to the side here. So there's some algebra that goes on between this step and the last one, which would be integral from alpha to beta. So you can see what I would have is 1 plus dy dt squared over dx dt squared. And what I'm going to do with this dx dt is I'm going to use that trick where I square it and put it under a square root. So dx dt squared, but also under the square root, and that way I can slip it under the radical. And I just have this dt outside the radical. And so what you'll notice is I'm going to distribute this into my radical. So I'm going to have to multiply it by that and by the 1. And when I multiply it by that first term, it's going to cancel the dx dt squared in the denominator. When I multiply it by the 1, it's just going to leave me with dx dt squared. And thus I get to this final integral, which is the arc length of a curve traced out by parametric equations. X equals f of t and y equals g of t can be found using this arc length formula. It's just integral of the square root of dx dt squared plus dy dt squared dt. Okay. Back to our cycloid, we're going to find the length of one arch of the cycloid given by x equals r theta minus sine theta and y equals r times 1 minus cosine theta. All right, we did some of this work in our previous example, and we're going to use some of the results for this. Which was, we found that in Cartesian, right, when we were trying to evaluate this arc in Cartesian coordinates, we would have integrated from 0 to 2 pi r. Whatever the function is in terms of x for that arch dx, right? But when we converted it to parametric, we had to convert our limits of integration to be in terms of theta. And so that's the work we did on the previous one. And we found that the limits of integration would be from 0 to 2 pi, right? Where one arch is traced out between the angles of 0 and 2 pi. And so we're just going to use that rather than, well, come on, catch up, computer. Rather than do it again. And I posted the video of that, so if you need to see where that comes from, you can go back and look at the video in last week's module of the example 2 that we went over on Thursday. All right. So basically right away I'm going to say, okay, I have my integral. My arc length is the integral from 0 to 2 pi, since that's the interval over which theta will trace out one arch of that cycloid. And now I'm going to do square root. It's going to be dx d theta, that's our parameter here, squared, plus dy d theta squared, and that's all with respect to theta. Okay, so just off to the side, let's real quick figure out what is dx d theta. Well, looking at x, remember that r is a constant, so that's just going to be r times the derivative of theta is 1 minus the derivative of sine is cosine, so cosine theta. And then dy d theta r is a constant multiple, I should say. So it just sticks there. Derivative of 1 is 0. Derivative of cosine is just negative sign, so I would have negative negative sign or positive sign. So it's just r sine theta. All right, so let's just put those in place. My integral becomes the integral from 0 to 2 pi square root of r times 1 minus cosine theta squared plus r times sine theta squared d theta. Okay. So we're going to simplify this where we can. One thing I can do, notice that both of these r's are going to be squared, so I'm going to just square them and factor that out. And then when I FOIL out the cosine, the 1 minus cosine, I'm going to have 1 minus cosine, no, 1 minus, sorry. It'll be 2 cosine theta. And then it'll be plus cosine squared. And then I'll also have plus a sine squared. D theta, right? All right, a couple things we can do. First of all, you have this r squared factor, so you can pull out an r. The square root of r squared is just r, right? So r root, nope, sorry. R integral, 0 to 2 pi, roots. All right, so that I know you guys are alive out there, in the chat, what can I simplify this piece to? What's sine squared plus cosine squared?
1.
Okay. So that just becomes a 1, and then I have plus this one. And calculus 2, we know that 1 plus 1 is, oh, very good. So I have 2 minus 2 cosine theta d theta. All right, if I factor out a 2, this actually looks similar to an identity that we have in our trig cheat sheet. So remember you have that half angle formula where all right, so here's the identity I'm going to actually use. It's a sine squared identity. And sine squared is 1/2 times one minus cosine of 2x. So we kind of have something that looks similar to this situation going on here, right? But what I'm going to do is, remember that 2x would equal theta in what we have. Oops, sorry, I just realized this should just be cosine theta, not cosine 2 theta. That was a mistake by me. So theta equals the 2x there. And so if I replace that, that identity can kind of become, whoops, sine squared of theta over 2 equals 1/2 1 minus cosine of theta. And if I multiply over the 2, I have 2 sine squared of theta over 2 equals 1 minus cosine of theta. All right, so now I'm kind of ready to make that substitution. I can replace 1 minus cosine of theta here with that 2 sine squared theta over 2 based on that trig identity. Okay. Zero to 2 pi, so I'll have 2 times 2 sine squared of theta over 2 d theta. And I still have that r out front. And apologies, this is all under a square root, right? But that little trick, that little identity made it easier for us to take the square root. So now this is going to be 2r integral 0 to 2 pi of just sine of theta over 2 d theta. All right, so the antiderivative of sine is negative cosine. But remember, we have an angle multiplier. It's actually theta over 2. So to compensate for that, I'm going to actually be multiplying by 2. You could technically figure this out with a u sub where you let u equal this. But we had done these in the past where we just remember you basically divide by whatever the angle multiplier is. That's what ends up happening, right? So I would take the antiderivative, which is negative cosine theta over 2. I would divide by the angle multiplier, so I would divide by 1/2. Dividing by 1/2 is the same as multiplying by 2. So I end up multiplying by 2 and I get basically 4r times this from 0 to 2 pi. All right, so 4r times negative cosine of pi when I plug in the upper limit minus negative cosine, so actually plus cosine of 0 when I plug in the lower limit. Well, cosine of pi is negative 1. So we end up with positive 1 plus 1. 4r times 2, that's 8r. So the arc length in one arch of a cycloid is just 8 times the radius of the circle that's tracing out the cycloid. So the last thing we're going to talk about is surface area for parametric equations. So we're going to suppose that this curve, given by these parametric equations...
Mr. Toller, you're muted.
Okay, so the last thing we're going to talk about is surface area. We're going to take the same parametric equations, x equals f of t, y equals g of t, where t is between alpha and beta. We're going to rotate it around the x-axis. And what we're going to look at is, this is just our regular surface area equation or integral, but now we've converted it once again to parametric equation. So it's 2 pi y and then times arc length, which we just converted arc length to parametric form. And so the only thing to remember, if this is in terms of t, y is equal to g of t, right? All right, so I'll write this out on the next page. do integral dx dt squared plus dy dt squared dt. All right, show that the surface area of a sphere of radius r is 4 pi r squared. So here's how we're going to create our sphere. We're going to remember that we can create a sphere using the parametric equations x equals r cosine t, y equals r sine t. Right? When the radius is just 1, it's just x equals cosine, y equals sine, and that creates the unit circle. Now, we don't need to use the whole circle. We're only going to use half of it, and then we're going to rotate it around the x-axis. So I'm going to say, let's let t be only between 0 and pi. So that's only going to trace out the top half of that circle. Right? And then what we'll do is we'll rotate that circle, or that semicircle, around the x-axis, and that'll create a sphere for us. And so let's just verify this in our calculator. It's been a little while since we've worked with these parametric equations. But I can go to mode. I'm going to change, make sure I'm in parametric mode. I'll go to y equals x1 we said is r cosine t. So let's just say we want a radius of, I don't know, 3. So then I would do 3 cosine t. I would do 3 sine t for y. I go to my window. I only want to trace out between 0 and pi. Keep my t-step around 0.1. And if my radius is 3, I don't really need to see out 10 in every direction. Let's just go 4 in every direction. So negative 4 to 4. Negative 4 to 4. And I'll graph that. Kind of looks oblong. Remember, that's just because your calculator has a rectangular screen. So if you do zoom square, z square, that fifth option, it'll sort of account for that and make it more circular. But there you can see I have that semicircle with radius 3, and it's just the top half. Alex, why is it r cosine t and r sine t? So that's just derivative. It's derived literally from the unit circle and triangles. So I can go over that real quick. Well, let's say we have a circle that has radius r. Right? So I can create a right triangle out of that situation, where this is theta. And I'll call this the x, and this is y. Then cosine theta is r over x, right? Adjacent over, I'm sorry, other way around, x over r. Adjacent over hypotenuse, x over r. So x equals r times cosine theta. And likewise, sine theta for this triangle. Sine is opposite over hypotenuse, so that's y over r. So multiply by r. And I can say that y equals r sine theta. And there you go. You got a pair of parametric equations where theta is our parameter. X equals r cosine theta, y equals r sine theta. Right? And so here I'm just replacing the theta with a t. That part doesn't matter. But that's where the parametric equations of any circle come from. All right. And so now we have this half circle formula. We're going to spin the half circle around the x-axis. That's going to create a sphere. And we want to find the surface area of that sphere. So here's our formula for surface area. Let's start plugging some stuff in. All right, we want to integrate from 0 to pi. It's going to be 2 pi times y. Remember that our y is r sine t. I'm going to replace y with r sine t. And then I have the square root of dx dt squared plus dy dt squared. So off to the side, let's go over here and just figure out what dx dt and dy dt are. So dx dt would just be the derivative of r cosine t, so that would be negative r sine t. And dy dt is the derivative of r sine t, so that would be r cosine t. But then we're squaring both of them, so they do both end up just being positive anyway. So I end up with r squared sine squared t plus r squared cosine squared t dt. There we go. That should get me the surface area of my sphere. Let's simplify. All right, integral 0 to pi, 2 pi r sine t. You can factor out an r squared. Then you're left with sine squared plus cosine squared. Again, we know that that just reduces to 1. So you're just left with the square root of r squared, which is just r. Integral 0 to pi, 2 pi r sine t times r dt. Pull out the 2 pi r squared, that's a constant. Antiderivative of sine is negative cosine. I want to go from 0 to pi. So negative cosine pi. This ends up being plus cosine 0. That's 1. That's 1. And boom. We've now proven that the surface area of a sphere of radius r is 4 pi r squared.